Binary digital modulations. As a preview to doing this performance analysis, we had discussed yesterday the properties of the sample output on the basis of which you are going to make decisions in typical binary digital demodulators, receivers, right? And specifically what we appreciated was that as far as coherent signals are concerned, we continue to work with either zero mean or non-zero mean Gaussian random variables, but for non-coherent receivers we may have to deal with other kinds of distributions like Rayleigh distributions and Rixian distribution, right? And we were in the process of doing a performance analysis based on these assumptions, that your channel is distortionless and the noise is additive and white Gaussian in nature. So it's an additive white Gaussian noise channel. I'm just quickly recapitulating what we did yesterday. So we'll assume the received waveform to be the sum of the transmitted waveform as such without any distortion plus noise with power spectral density as given here, n0 by 2, and the demodulator consists of the match filter. We are looking at coherent receivers first, so it consists of the match filter, no envelope detection, just the match filter output is sampled at every bit interval, at the end of every bit interval, and this is followed by a threshold detection operation, right? Let's denote this sample value by x, which becomes our decision statistic, okay? And what you have to appreciate is that this x will have in general different distribution when a 0 is transmitted and when a 1 is transmitted, right? They may be different only in means. If they are all Gaussian, they may be different only in means, for example, but they will be different, right? So we will denote by p sub 0x as the PDF of x when 0 is transmitted and p sub 1x PDF of x when 1 is transmitted. I think this is the point at which we stopped yesterday, and we'll start from here today. Any questions on this? Fine? Okay. So this is a picture for that. Okay. I think I'll start with a slightly different picture, which is here. We have another one. Yeah, I think that's okay. So I have displayed here as an example the case of coherent on-off keying, right? The match filter output in this case will be a zero mean random variable, zero mean Gaussian random variable when a 0 is transmitted, because in that case the match filter is getting only noise at the input. When you have on-off keying for a 0 transmission, nothing is being transmitted, right? So the match filter output when sampled at t equal to kt will only be a zero mean Gaussian random variable, which is the distribution p0x shown over here. All right. When a 1 is transmitted, what is going to happen to the match filter output? It will be shifted in mean. The distribution will be shifted in mean by an amount, let's say equal to a, where a is the amplitude at the output of the match filter. All right. So we'll have a amplitude due to the signal. The noise will continue to be governed by this distribution as shown here, except that the mean is shifted to a, right? So the random variable x which you are looking at either has this distribution or has this distribution, right? So if it has this distribution, you know, typically this is a range of values over which x will go, right? Well, typically with a average spread equal to the variance and things like that. When signal is coming along, when a 1 is transmitted, the range of x of values of x that you will typically see is governed by this distribution, and our decision on whether a 0 or 1 is transmitted is going to be on the basis of comparing this value of x that you have observed on the basis with the threshold value theta, right, which I have arbitrarily shown to be here somewhere between these two distributions, right. Obviously it has to have a location of the kind that I have shown here, so that we don't make too many errors, right, and the error probability in terms of these curves is shown by the two shaded areas. For example, this blue shaded area, right, from here towards minus infinity this side, this gives the probability that error occurs when a 1 was transmitted, but you are wrongly thinking that a 0 has been transmitted, right, because although we are considering this distribution, that is the distribution corresponding to transmission of a 1, this small little shaded area in blue is the probability of the event that the value of x will still turn out to be less than the threshold, and therefore will make a wrong decision that a 0 was transmitted. Is it okay? Similarly, the black shaded area is the probability of the error when a 0 is transmitted, right. That is, your x is really governed by this distribution, but the noise at the match filter output, the noise sample at the match filter output turns out to have a value larger than the threshold that you have selected, and therefore the probability of that event, which is the shaded area shown here, is the probability PE given 0, right. So these are the two kinds of errors that we can have, a 0 going to 1 and a 1 going to a 0 with the corresponding probabilities as shown by these two shaded areas.
So have you deliberately shown PE 0 to be greater than PE 1?
No, I have not deliberately shown. This is the point I want to discuss, so I will just come to that point now. The question then naturally comes, where should this threshold be, right? This is one of the important things you will have to worry about. Where should you locate the threshold?
Least error
problem. There are several ways by which you can look at this problem. One typical approach is, well, obviously our overall interest is to minimize the total error probability, right? And what will be the total error probability? Well, you might like to say that it is this plus this, but you have to be careful. These are conditional probabilities, right? The total error probability will be half of this plus half of this, right? Let me write down a few things and I will come back to this discussion of how to select the threshold. Let us go through a bit of maths and I will come back to this picture again. So let us denote by theta the threshold value as I have shown there. Then mathematically the two error probabilities are error when a 0 is interpreted as a 1, that is you actually transmitted a 0 but an error occurs, right. That will be governed by the distribution, that will be governed by the tail of the distribution of P0x, right. P0x integrated between theta and infinity, right, dx. Similarly, PE given 1 will be the area under P1x between minus infinity and theta. Now, from the point of view of minimizing the total probability of error, assuming that both 1s and 0s are equally likely, what can you say about the location of theta? Can you make an intelligent guess?
It should be at the crossing.
It should be at the point of intersection. It's obvious?
C1 is, yes, we can differentiate this. That
It's
P1x
obvious.
is equal to P0x. The point.
Yeah, that is one way of doing it. The other way is this picture automatically shows it, isn't it? Isn't it obvious from this picture
Yes, sir.
that the minimum probability of error will occur when you choose the threshold to be at the crossing point?
Yeah, because
It's not obvious?
Is that
No, mathematically it is.
Yes.
No.
You are adding that much area extra.
Very good, you have got it right. You see, if you put it here, What is the area that you are considering? The area under this tail here and area under this tail here. If you put it anywhere else, you will anyway have all this area, plus you will be adding some more area to this, either this way or this way, right? So that is the logic which makes it obvious that from this point of view, from the point of view of minimizing the overall error probability, particularly when zeros and ones have equal probability of transmission, right, the optimum threshold should lie at the point of intersection of these two distributions. You can even, as Varun has rightly said, differentiate these two areas and mathematically check that indeed that will be the result. However, occasionally people use a different criterion for selecting the threshold, occasionally, depending on your application environment. Occasionally, rather than making sure that the total error probability is minimum, sometimes you just like to make sure that the number of ones and zeros that the probability of declaring a 1 into a 0 and the probability of declaring a 0 into a 1 have equal values, so that at the receiver output ones are not, there are not too many ones as compared to zeros, and there is no bias for ones or zeros, right. So occasionally you may have a different criterion, but in most of the situations one uses the criterion which I just mentioned, and it makes for symmetrical distributions it anyway doesn't make any difference which criterion you select, right, because if these two distributions are symmetrical and have identical variances, it's obvious that if I put the threshold here, not only will I have minimum probability of error, but also the two kinds of error probabilities will also be equal, right.
If you assume that they have the same variance and distribution is absolutely
That's right,
except for the mean.
except for the mean, which is the case for most of the coherent situations, right? But non-coherent situations, that situation may not apply. We will see that. So is that fine? All right, let's proceed with the. So usually the threshold theta is selected either to minimize let's say half p is 0 e by 0 plus, right, or simply make p e 0 q1 0 equal to, right. One of these two criteria is typically used, and for symmetrical distributions the two criteria will turn out to be the same. Now while proceeding further, you notice that we will have to evaluate these two areas to obtain the expressions for these two error probabilities. We will have to evaluate the areas under these tails, right, of the Gaussian distribution. So the area under the tail of a Gaussian distribution is a very important function with which we will have to continue to work for developing expressions for error probability. I am sure you are familiar with that function, but just to complete the discussion, let me define for you an integral q of x. It's called the q function, which is the integral of this kind, 1 by root 2 pi. Basically take the standard Gaussian distribution. Let me make it y here because I have put x here, all right. Take the standard Gaussian distribution, the value of the integral from x to infinity, which is the area under the tail of the distribution from x to infinity, right. That is called the q function. Now this has not exactly this, some related functions have been widely tabulated. This is an integral which you cannot evaluate in a closed form, right. This has to be evaluated numerically, but asymptotically for large values of the argument x here, that is when you are looking at the real tail of the distribution going very far away from the mean, this can be approximated by e to the power minus x squared by 2 upon x into square root of 2 pi for large values of x, okay. Now qx is related to a very standard function in maths, which is known as the complementary error function. I'm sure you're familiar with the complementary and the basic error functions. It's denoted by ERFC, argument is x, and defined as 2 by square root of pi x to infinity e to the power minus y square by 2 dy. And this is complementary error function because this is actually defined in terms of another function which is called the error function. 1 minus the error function is this function. Okay. This function, the error function, has been widely tabulated in maths, so one can obtain the values of this function error ERFCX from those tables, and therefore the value of QX also from those tables. You can see there is only a scaling factor difference between the two, right? So this is widely tabulated. Between Qx and this, here the scaling factor is 1 by square root of 2 pi, here it is 2 upon root pi, otherwise everything is same. Right? So now with this background, let's take up specific modulation schemes and try to do some analysis. And the first one I'll take up is binary phase shift keying. Even that example of on-off keying that I have discussed is only from the point of view of illustrating the approach. Now we are taking up the calculation for BPSK. Alright, for BPSK the situation is very simple. It has to be a coherent demodulator, right? That means we are basically looking at match filter followed by sampler followed by. So what are the two distributions that will be coming to the picture here? Both will be Gaussian, but it's an antipodal modulation scheme. So under the situation when a 0 is transmitted, we expect the match filter output to be minus A, right? Because the signal that is transmitted is either A cosine omega naught t or minus A cosine omega naught t. Match filter will be matched to a pulse, or RF pulse cosine omega naught t, and you're going to sample the peak value of this output. That will be either plus A or minus A, right? So basically you're going to have P0x as a Gaussian distribution with mean of minus A, and P1x as a Gaussian distribution with a mean of plus A, where A represents the amplitude of the output pulse at the output of the match filter. So I think the calculation is straightforward. Obviously the threshold should be selected at x equal to 0, right? That is, you are looking at the match filter output at t equal to kT and comparing it with a threshold 0. If it is positive, is greater than 0, we will declare a 1. If it is negative, we will declare a 0. And the shaded areas are the two kinds of error probabilities we have discussed. Okay. So what is P0x here? Mathematically we have 1 by root 2 pi sigma e to the power minus x plus a whole square by 2 sigma square, and P1x is same thing except that the mean is A, where A is the sampled output of the match filter and sigma square is the noise variance, which is equal to n0 by 2. Any questions? Fine. So what will be your PE 0? PE given 0 is the integral from 0 to infinity of 1 by root 2 pi sigma, which distribution, e to the power minus x plus a whole square by 2 sigma square dx. Is okay? Divided by where? Oh, that is when I consider the total error probability, then I'll write half of this plus half of that, right? But this is the probability of making an error when 0 was transmitted. This is a conditional probability, right? From conditional probability, when we come to a complete probability, we'll bring in that factor of half using Bayes' theorem and all that, right? Fine. Now, whenever you have integrals of this kind, the typical way to handle things would be to put it back in the standard form, and then you will be able to get it in the form of in terms of the Q function or the error function, right? And typically the way you will do it is define a new variable y, let's say equal to x plus a upon sigma. If you do that, what will be the value of this integral?
Error function at x equal to a.
Now let's go through the thing. What will be the lower limit with respect to y? A by sigma, right? The upper limit will be infinity, and it's obvious that this will be now, because dy will be equal to dx by sigma, right? So dx by sigma can be replaced with dy. So 1 by root 2 pi sigma will disappear, minus y square upon 2. So now that's precisely in the standard form, and this x is to be identified as a by sigma. So this is nothing but the value of the Q function evaluated at a by sigma, right? It's obvious from the symmetry of the problem that P E given 1 also will be the same, isn't it? It's obvious that these two areas are equal, whether I consider this area or this area. So both, I don't have to do the computation again, which is also equal to P E given 1. Fine. Therefore, your total probability of error, which I will just denote by P sub E from Bayes' theorem, is the a priori probability of 0 transmission multiplied with the corresponding error probability. Similarly for this, which essentially means half of this plus half of this, which is again Q A upon sigma. Now, what is your A upon sigma? Remember, your A square by sigma square, the SNR that we discussed at one time, is 2 E sub B by N0, right? Because we discussed that before, let me not discuss it again. Therefore, your P sub E is square root of this quantity. Q function evaluated at okay. That is the mathematical expression to describe the error rate or the error probability for binary PSK, the precise mathematical expression, which for large values of the signal to noise ratio, when EB by N0 by 2 is large, right, can be approximated by the asymptotic formula we discussed as this quantity. For large SNR. And you might observe that the asymptotic behavior is really governed by this factor e to the power minus E sub B by N0. That is, asymptotically, as the signal to noise ratio is made larger and larger, the error probability can be made smaller and smaller, approaching 0, right? So asymptotically, is governed by this vector largely. If you were to plot this curve, that is error probability versus the signal to noise ratio, and you will find in typical curves of this kind, typical error rate curves, the basic parameter against which curves are plotted is this quantity EB by N0, right? Because this is a fundamental thing which you can extract from your transmitted signal and compare various modulation schemes on the basis of same EB by N0. That is for a given signal energy, for a given noise variance that you have to deal with, that is for a given match filter output, what is the various kind, what is the error rate. So you will find typical error plot curves as shown over here. You only have to concentrate on this curve at the moment because I have not discussed the other modulation schemes yet. So EB by N0 is along this axis. This has been taken in dBs, right? These are some right, some typical values and some typical values of the what I have called bit error probability, right? And again they are on a log scale, as you can see. Both this as well as this are on a log scale, right? Because otherwise you can't put them nicely in a small picture like this. So typically this is error probability of 10 to the power minus 4. That is, you expect if you choose this error rate for design, what you are saying is 1 bit in 10,000 bits is allowed to go in error, not more than 1 bit in 10,000 bits, and so on. 1 in 1000, 1 in 100, 1 in 10, right? So typically what you will see is, let's say for an error rate of 10 to the power minus 4, you require an SNR of something like 8.4 dB, 8.4 decibels, right? For an bit error rate of 10 to the power minus 4, this point is around 8.4 dB, right? So this is a standard curve which becomes a benchmark for comparison with your actual performance which you obtain for your system that you have designed, right? Of course, in reality, even if you were to use coherent PSK, your error rates will be higher than this, slightly higher than this, because of various imperfections you may have in the system. But this becomes a benchmark for you to compare how badly you are with respect to what you could have done ideally, right? Now let's go to, is there any question about this before I go into the next binary modulation scheme? So it's the performance analysis is quite simple for the case of BPSK. Let's do the same thing for on-off keying now. Now one can go and repeat the whole exercise as we have done for BPSK, right? But one doesn't have to do it. One can derive the result for binary on-off keying from the result that we have for binary PSK very easily. Yeah, the only difference is in one case the P0 and P1 have mean minus A and plus A, in the other case they have 0 and A, right? So one can go ahead and do it and obtain the expression which you can do and verify the result that I am going to tell you. But another way of looking at it is the following. No matter whether you are using BPSK or on-off keying, the noise variance at the output of the match filter in each case is same, right? Because the two distributions and everything else we are assuming all conditions are same. So at the match filter output, the noise variance remains that N0 by 2 or whatever. Right? That is same as in BPSK. It's the signal outputs which differ in the two distributions, right? In one case, in the OA on-off keying case, signal output is 0 or A, depending on whether you transmitted a 0 or transmitted a 1. and the difference between the two means is A, right. That means the performance of this scheme would be this, with this difference would be the same as that of a binary PSK system with amplitudes of minus A by 2 and plus A by 2, right. Is that clear? So therefore performance would be same as that of BPSK with signal outputs at match filter as minus A by 2 and plus A by 2, right. So therefore as far as that is, if I have this situation, on off keying with amplitude A and BPSK with amplitude minus A by 2 and plus A by 2 are the match filter outputs, I will get identical bit error probabilities, right. Now I want to convert that into an expression for the error rate. What we can do is we can look at what is the signal to noise ratio here and what is the signal to noise ratio here in this situation, right, and that gives us a simple way of obtaining the expression, right. What is the signal average energy that you transmit here? Average energy per bit for the case of BPSK would be how much? Is proportional to A by 2 square, right. Let's call it A square by 4. For the case of, isn't it? Equivalent BPSK, which gives you the same error probability, right. Similarly, average energy per bit for the case of on off keying is proportional to half A square, right. So what we can say is that performance of OOK is equivalent to that of BPSK with how much SNR? With 3 dB lower SNR or half the SNR, right. So now tell me, how can I write P sub E? It will be Q function evaluated at, it was that's right, EB by N naught. It was 2 EB by N0 for PSK, right. For the same error probability it becomes or for the same SNR it becomes corresponding to half of that SNR, right. So is the argument clear? Of course one could obtain this expression in the normal way that we did for BPSK, there is no difficulty about that, but this gives you a feel for a comparison between on off keying and phase shift keying in the coherent case, that to obtain the same probability of error in the two cases, on off keying would require 3 dB more power than phase shift keying, is something that we are try to appreciate much earlier intuitively, but now we have a very clear mathematical understanding of what that means. When we say that on off keying is an inefficient scheme, it does not use the power efficiently, now we have a very clear idea how it does not use the power efficiently, right. That is, we are unnecessarily wasting 3 dB of power as compared to BPSK, with unnecessarily transmitting twice as much power for getting the same performance, same error rate. So if you look at the curves, this is a curve, this next black curve is the one for both coherent FSK as well as coherent OAK, but I will discuss FSK separately, right. At the moment you look at OAK, what you will find is that if you were to draw a horizontal line anywhere, right, the corresponding SNR readings will be separated by 3 dB, if you were to draw a horizontal line anyway for any error rate. So the curve is higher than the PSK curve. For a given error rate, the on-off keying would require 3 dB more SNR as compared to the corresponding PSK. That is the conclusion of our discussion, right? So if I draw a horizontal line anywhere on this curve, the 2 points on the 2 curves will be separated by 3 dB along the x-axis, right? Any questions? No questions? Okay, good. So we have the expression for BPSK, we have the expression for coherent on-off keying. We now come to coherent, non-coherent on-off keying. That's slightly more involved, but not really all that much. Let's. Okay. Before going, sorry, I have to do one more coherent scheme before I go to non-coherent schemes, and that is coherent FSK. The coherent FSK has the same kind of performance as coherent on-off keying, but for different reasons. Can you guess what is the reason?
The distance between the two signals is equivalent to that
Is equivalent to that of?
for the same energy.
Let's now talk in terms of match filter outputs, because the way we are doing the processing we have to see, right?
So the output is 0 or 8 from match filter. Not 0, it can be both can be different A and B.
I think the best way to look at it is, if you remember, we have two coherent match filters, one corresponding to each of the two waveforms, and then we are taking the difference of these two, right? And then comparing it with the same kind of threshold problem like in BPSK, right? Now, what is going to, let's say one of them contains, the signal is one of those signals, one of the two match filter signals, then the correct match filter will produce a output with a mean of A, right? And the other one will be just noise with
0.
So what are you going to do? You are subtracting the two.
A or minus.
The result of subtraction will produce an output which has a mean of either plus A or minus A, depending on whether the top filter or the bottom filter produce the amplitude A.
But we have double energy. So.
But the noise variance is twice as much, because the two noises in the two orthogonal match filters are uncorrelated and independent. I don't have the picture here, but I think, let me write it down. So in this case we use two match filters, orthogonal match filters, right? And these two match filter outputs are being subtracted from each other before being applied to the threshold detector, right? The process of subtraction basically adds the noise variance, increases the noise variance by a factor of 2, right? So the decision statistic that we are working with, X, which is a difference of the two match filter outputs, only one of them has a signal and the other has only noise. One has signal plus noise, other has only noise, right? You have one match filter here, another match filter here. One is producing signal plus noise, the other is producing only noise, and the noises are independent. You are subtracting the two, right? That's what you are doing. This subtracted value if you look at this value as x, the subtracted value, then the mean value of x is obviously either plus a or minus a, right? Precisely the same situation as in BPSK. The mean value in BPSK is also either plus a or minus a, clear? But the noise variance, noise power is twice as large. That is the essential point to appreciate, because both these noises have equal variance and are statistically independent. When you add them, basically you are adding, or you are reducing a random variable with twice as much variance. Okay, that's very elementary statistics that you are familiar with. And therefore, your expression for P sub E your noise variance becomes from n0 by 2, it becomes n0 effectively. So, EB by n0 as before. So, which is the same expression that we had for coherent on-off keying. Of course, from another point of view, we expect them to behave similarly, because we can in some sense say that both are orthogonal modulation schemes, right? So, they have identical performance. Okay. Now, let us come to non-coherent situations, and the simplest to consider is, of course, we can't have non-coherent BPSK, right? So, we do not consider that. We consider on-off keying case, whether for coherent case or for non-coherent case, is being considered only out of academic interest, and also because it helps us to understand things in a proper perspective. You must understand, we do not use on-off keying in almost any application these days. So, it is just for the purpose of developing our analysis nicely. And again, non-coherent on-off keying, just for the sake of completeness of discussion, we are going through it. Very rarely it is used. Now, if you remember, your non-coherent on-off keying receiver was something like this at the baseband, right? That is, you have the baseband output coming out of the IQ demodulators, right? And we are assuming that your transmitted signal is A times ST, right? Or it is either there or not there, either with amplitude A or with amplitude 0. So, this complex input signal is being passed through, both the real part as well as the imaginary part is being passed through S minus T, the ST T minus T naught minus T, the match filter corresponding to ST, and these two outputs are being combined by envelope detector I square plus Q square square root of that, sample and output. So, this was, I know you remember this, but just to make you precisely understand what is happening. Basically, therefore, if you look at this input here, this output of the two match filters, you have two random variables, right, and we can describe them by a two-dimensional Gaussian distribution function, because both are individually Gaussian. And remember, what is this output like? AK cosine theta plus j times AK sine theta plus noise, right. So, this is AK plus noise, this is also AK plus noise, actually AK cosine theta, this is AK sine theta with noise independently there. Therefore, you can think of the two variables x and y. If I call this x and call this as y, the real part is x and the imaginary part is y, right. We have a joint distribution of x and y, both have, this means you are considering a two-dimensional distribution, both are individually Gaussian. So, it is a joint Gaussian distribution of this kind, and either if you are transmitted as 0, both of them will have 0 mean, x as well as y will have 0 mean, because the input is containing only noise, both the inputs, right, because this is a complex representation of your actual input. If actual input contains only noise is going into both of these, right, and therefore both x and y will be 0 mean. Clear? On the other hand, when a signal is coming along in the pulse duration, they will have non-zero mean, and the means will be ak cosine theta and ak sin theta. In this case it will be ak cosine theta, in this case it will be ak sin theta. So you can think of in the xy plane a 2D distribution which for 0 transmission has a 2D density function, 2D Gaussian density function like this, and for a 1 transmission has a Gaussian density function whose mean is ak cosine theta along x and ak sin theta along y. So somewhere here. So the same distribution function has been shifted here, right. So this is the PDFs which come into the picture for non-coherent on-off keying. Let's see what we would have done in the case of coherent on-off keying in this picture. In the coherent case, we would have somehow known the value of theta, right? Right? This theta would have been known to us, and therefore I could have aligned my let's say the x-axis by rotating it by along this direction, and the value of the imaginary component would have been superfluous and of no use to us, right. This is what we do in coherent on-off keying, any coherent system, because when we do that carrier compensation e to the power j theta multiplied by e to the power minus j theta, essentially what we are doing is we are aligning ourselves with this axis over here which separates the two density functions at this line, and then only how the variable behaves in one dimension is enough. We don't have to look at the other dimension, which is what we did just now, right. But right now when we do non-coherent situation, the parameter which is important is the radial distance or the distance of the observed value from the origin, right, because we are going to say if that is what envelope detector does. It will really not look at just along this line, it will look at what is the observed value along x, what is the observed value along y, and it can compute a radial distance from the origin, whether it is from this distribution or from this distribution, right. And that radial distance from the origin we have tried to appreciate last time, either has Rayleigh distribution in this case or has a Richian distribution in this case, right. This is what we try to appreciate. In other words, we are now governed by a distribution function of R which is square root of x square plus y square, right, which has for a 0 transmission a distribution like this which is Rayleigh, and for a transmission of a 1 has a distribution like this which is Richian, right, which for large SNRs we know resembles a Gaussian distribution function. So that is the picture we really have to consider, because we are working with R, we are not working with 2 dimensions directly. We are converting the 2-dimensional x and y into a variable r, right, a scalar variable r which is square root of x square plus y square, which is governed by these two distributions. Again we can choose a threshold appropriately and go ahead and do the error probability calculation. So conceptually, is there any problem for the case of non-coherent on-off keying? I will just go through a few mathematical steps, and I will not really do the complete analysis in this case for 2 reasons. One is it is only of academic interest, and second is because the 2 density functions are different. In one case you have Rayleigh, in the other case you have Richian. Determination of the optimum threshold as well as the corresponding error probability become fairly involved, just algebraically involved exercises, which I don't want to waste time on. You can read about it yourself, a page or 2 from the books. and I'll just like to basically give you the performance curves that you have corresponding to this. What do you expect? The performance to become better or worse than coherent on-off pinging? Worse, because you're not making use of the phase information, and that's precisely what you have here. This black dotted curve is what you get for non-coherent on-off ping. Okay. Now, non-coherent on-off keying is, we already seen it is not very good because it wastes 3 dB of power for you. You require 3 dB more power, but you could say that FSK also uses 3 dB more power, and still in some systems we do use FSK, even binary FSK. How come we have such a strong disliking for on-off keying that we don't use it at all, whereas we continue to bear this non-coherent FSK? Coherent FSK or non-coherent FSK? We have to discuss non-coherent FSK still. We have only discussed coherent FSK, right? I'll discuss non-coherent FSK next time because I don't have time now. But between these two, how come one of them we totally reject and the other we still continue to work with? Can you give any argument?
DC null.
DC null. No, from the performance point of view, do you have any reason to give? From this curve point of view, can you see?
So you're comparing coherent OIK with coherent FSK.
Non-coherent.
Actually,
So what is-
on-off keying with frequency shift keying, whether coherent or non-coherent. Right? Let's take the case of coherent on-off keying. Something that should strike you immediately from these plots that I've got.
Unequal probabilities of fair component.
Yes, sir. Threshold is very sharp.
Most importantly, the fact that the threshold depends on
Very
the
sharp.
amplitude. That fact is the single factor which creates a lot of trouble for us, because we have to know a priori what the signal amplitude is going to be, right? Which is very, very difficult for a receiver designer to work with. He doesn't know what amplitude to design the receiver for, how to set the threshold, or he has to experimentally do it as the signal is being received, right? Because you don't know what your received signal amplitude is going to be exactly, right? Particularly in a fading channel, let's say, where the amplitude may be even time varying, received amplitude may be even time varying. If the deep fade occurs, occasionally the amplitude may become very low, and occasionally it may reinforce itself, right? So the fact that your optimum threshold depends on, because it has to be somewhere in the middle of this and this, whereas in binary PSK, or in fact for that matter for FSK, after you have done the subtraction, the threshold is always fixed at 0. It is independent of the signal amplitude which is received. So that is one of the single most important factors, other than the ones which we have discussed earlier, which also discourages the use of on-off keying in practice. I think this is a good stopping point for us. We will continue with this discussion.